Io sono Sergio Palazzo dell'Università di Catania, per chi non mi conoscesse. È inutile dire che essendo referente scientifico per la partecipazione dell'Università di Catania al programma PNRR Start, nonché responsabile dello SPOC numero 6, sono molto onorato del fatto che ci è stato chiesto di ospitare questa Plenary Dissemination Workshop, cioè il momento in cui midterm si presenta un po' lo stato dell'arte dell'attività scientifica svolta nel programma e si dà un quadro anche di quello che avverrà nel prossimo anno e mezzo di vita del programma stesso. Direi che io vorrei ringraziare in questa occasione tutti i colleghi dell'Università di Catania che hanno lavorato insieme a me in questi giorni per la preparazione. Pronto? Sì, va bene. Per la preparazione di questa kermesse. In realtà è stata una kermesse perché abbiamo di fronte 2 giorni di plenary workshop. Ieri c'è stato un altro workshop che ha avuto la sponsorship del programma Restart su Open Network Intelligence for Connected and Autonomous Vehicles. Quindi un grande lavoro che è stato possibile, continuo a dire, grazie al supporto di tutti i colleghi, soprattutto i giovani colleghi, gli RTDA e gli studenti di dottorato che il programma PNRR ha dato l'opportunità di assumere, nonché il personale amministrativo del Dipartimento e dell'area della ricerca dell'Ateneo. E ancora vorrei ringraziare anche il personale del CNIT, del Consorzio Nazionale Interuniversitario per le Telecomunicazioni, che ha curato tutta la parte di registrazione e di supporto all'organizzazione. Il tempo è tiranno, vorrei dare inizio a questo punto ai lavori e il primo intervento è quello del magnifico rettore dell'Università di Catania, Francesco Priolo, che è qui accanto a me. Gli passo subito la parola, poi parlerà il dottor Fabrizio Cobis, che come sapete tutti è il responsabile, il RUP da parte del MUR per tutte le attività dei programmi PNRR. Vabbè, mi sia consentito dire un ringraziamento a Fabrizio Cobis non solo per essere venuto ancora una volta qui a Catania in questa occasione, ma anche per la costante attenzione che riserva alle nostre attività, insomma, no? Direi quasi paterna, nel senso che da una parte dà sempre suggerimenti, dall'altra, come ogni padre che si rispetta, sa anche essere severo in certe occasioni. Va bene, do la parola al professor Francesco Priolo. Grazie.
Grazie Sergio, e davvero un caloroso benvenuto a tutte e a tutti presso l'Università di Catania. Anch'io mi unisco ai ringraziamenti, innanzitutto al dottor Fabrizio Cobis. Grazie Fabrizio per essere qui con noi anche oggi e davvero per tutto quello che stiamo facendo insieme in questi anni importanti per le nostre università, ma importanti per il Paese. Un ringraziamento alla Fondazione Restart, al suo presidente Blefari Melazzi, al coordinatore scientifico, al professore Capone e a tutti voi per aver accettato e aver scelto Catania come sede di questo meeting di midterm del partenariato esteso. È per noi una occasione di orgoglio potervi ospitare e poter fare il punto della situazione su quello che si è fatto e su quello che si farà all'interno di Restart proprio qui a Catania. Qui a Catania con ormai due dipartimenti di ingegneria che hanno festeggiato da un po' i 40 anni, hanno una storia importante e quindi diciamo davvero per noi è un grande piacere potervi avere. Restart. Intanto il nome, il titolo, non devo dirlo a voi che lo avete scelto, mi sembra particolarmente significativo per il Paese. Restart, ripartenza e in questo caso in un campo strategico, stiamo parlando delle telecomunicazioni, un campo strategico per il Paese, un campo strategico, non devo dirlo a voi, io sono un fisico, quindi diciamo sono molto vicino, mi occupo anche di fibre ottiche e di amplificazione, quindi diciamo sono vicino a quello che voi fate e non sta a me evidenziare quanto sia strategico e fondamentale investire sulle telecomunicazioni ed in particolare investire sulle telecomunicazioni del futuro. Ma investire sulle telecomunicazioni del futuro così come in altri progetti PNRR significa investire sui giovani e quindi tanti dottorati di ricerca, tanti ricercatori a tempo determinato all'interno dei nostri SPOC, dei vari SPOC, dei diversi progetti che stanno facendo, fatemi dire, un lavoro particolarmente fondamentale. Particolarmente fondamentale perché con i dottorati all'interno dei progetti PNRR, con i dottorati innovativi, sempre PNRR, che si mettono on top rispetto ai progetti PNRR, con i ricercatori a tempo determinato all'interno di questi progetti, quello che stiamo facendo in tutta Italia è di avere dei contatti diretti tra i nostri giovani e le nostre giovani direttamente in periodo di formazione con università e aziende, università e imprese. Un legame che è un legame strategico in quanto troppo spesso, e questo lo sappiamo benissimo, troppo spesso la ricerca, non solo in questo Paese, in Europa, non riesce poi a sfociare in reale innovazione. È ricerca ad altissimo livello, ma crolla prima di diventare innovazione. E per non crollare prima di diventare innovazione e poter transitare in quella che molti chiamano la Death Valley delle idee, dove poi le idee muoiono e non riescono ad arrivare sino in fondo, è fondamentale, scusatemi il bisticcio di parole, è fondamentale poter avere dei contatti sin da subito tra quelle idee e la parte delle imprese. Questo è quello che state facendo, questo è quello che stiamo facendo in tutto il Paese. È ovvio che al midterm, caro Fabrizio, una delle domande fondamentali è non solo quello che abbiamo fatto, non solo quello che faremo nel prossimo futuro, ma è che continuità vogliamo dare al Paese, perché dobbiamo sì restart, ma il motore lo dobbiamo tenere acceso. E allora diciamo riuscire a mantenere il momento e in particolare fare in modo che i nostri giovani, le nostre giovani che stiamo formando, che si stanno formando in maniera così importante, possano effettivamente essere per loro e per tutto il Paese un valore aggiunto, significa pensare anche al futuro. Quindi diciamo telecomunicazioni del futuro, ma anche ricerca ed innovazione del futuro, e io credo che in questi 2 giorni, oltre ad analizzare la parte tecnica, analizzerete anche come una fondazione del genere potrà spendersi sul dopo PNRR per proseguire ad essere un vantaggio importante per il Paese, perché quello che è successo, e dobbiamo dirlo in maniera forte ed importante, è che in tutti i campi finalmente, oltre alle cose che ho già detto, Finalmente il paese, le università e le imprese, ma le università anche tra di loro, si sono messe a collaborare in maniera importante. C'è un humus, una collaborazione, una conoscenza, uno scambio di conoscenze che sta portando un avanzamento della ricerca, della conoscenza, eccetera, che non c'è stato e non c'era a questi livelli nel passato. È ovvio che lo sforzo è uno sforzo immane. Io vedo qui il nostro dirigente alla ricerca, il dottore Caruso, che non mi stancherò mai di ringraziare, ma ciascuno nelle nostre università avrà un riferimento analogo, perché lo sforzo, Fabrizio lo sa, lo sforzo che ci chiedete è uno sforzo, direi, sovraumano, ma lo stiamo portando avanti con tutte le difficoltà del caso, lo stiamo portando avanti e io credo che si stia portando avanti bene. Mai essere soddisfatti, perché nel momento in cui uno è soddisfatto vuol dire che le cose, diciamo, da quel momento si crolla, quindi è cercare di puntare sempre meglio. Però via via stiamo portando avanti la spesa, via via stiamo portando assolutamente avanti la ricerca. Io mi fermo qua perché non siete venuti per ascoltare me e non posso che augurarvi una 2 giorni fruttuosa proiettata verso il futuro. Grazie.
Buongiorno a tutti, buongiorno al magnifico rettore, al professor Blefari, al professor Palazzo, a tutti all'Università di Catania che ospita questo momento di incontro così significativo e così importante e ringrazio per avermi dato l'opportunità di partecipare, sia pure brevemente, ma insomma ci tenevo perché insomma quando siamo normalmente a metà di un percorso è corretto il ragionamento, si fa un punto della situazione, si cerca di capire fin dove siamo a questo punto e cosa ci aspetta nella seconda parte della nostra attività e anche dopo. Benissimo parlare sicuramente dobbiamo parlare sia del dopo PNRR, sempre ammesso che si arrivi vivi e sani e salvi alla fine del PNR, però sono 2 cose strettamente importanti e devo dire che è molto suggestivo anche ragionare su quanto si è riusciti a fare finora, perché noi non ci dobbiamo mai dimenticare da dove siamo partiti. Noi siamo partiti 2 anni fa, 2-3 anni fa, con un'ambizione enorme, cioè quella di impiegare una mole enorme di risorse in un certo modo, con una certa logica. Qui non c'era soltanto l'occasione irripetibile di utilizzare tantissime risorse per investimenti in ricerca, ma si è voluto creare qualcosa che non c'era, si è detto correttamente, una capacità di collaborazione tra mondo universitario, mondo delle imprese e altri soggetti esteso come mai si era visto in passato, ma anche col tentativo di mettere insieme culture diverse, attività diverse. Ognuno di questi grandi programmi progettuali, parliamo di operazioni che vanno da 120 a 300 milioni di euro, vedono dentro numeri enormi di istituzioni, attività completamente diverse, ricerca, formazione, trasferimento tecnologico, creazione di impresa, infrastrutturazione, e quindi col tentativo di non fermarci alla parola collaborazione, perché poi la collaborazione in qualche modo sì, poi c'è sempre stata, qui si è voluto alzare un po' il livello, cercare di parlare di interazione, di contaminazione anche tra mondi e culture diverse, ma anche sul piano più gestionale, organizzativo. Qui si è partiti con la consapevolezza che avevamo 5 miliardi di euro da impiegare, sapendo che dicembre 2025 vanno completati. Va completato l'investimento dal punto di vista scientifico, dal punto di vista economico-finanziario. Questo significa che anche due mondi come quello di chi si occupa di ricerca e di chi si occupa più di aspetti amministrativi, tecnico, gestionali, procedurali, hanno dovuto imparare a parlarsi, a dialogare, a comprendersi, ad accompagnarsi l'uno con l'altro, e vi assicuro non era scontato, non era semplice. E quindi oggi uno ha la sensazione, anche partecipando a queste occasioni, di aver contribuito a creare delle vere e proprie comunità che si sono messe in cammino 2 anni fa su strade completamente sconosciute, piene di ostacoli, che continuano ad essere piene di ostacoli e piene di problemi. Però se guardo a come siamo oggi rispetto a come eravamo 8 mesi fa, un anno fa, io devo dire che da tutti i punti di vista sono stati fatti passi da gigante enormi, dal punto di vista proprio dell'approccio anche culturale alle operazioni, all'investimento, al rapporto con l'amministrazione. Noi stessi come pubblica, come Ministero, abbiamo imparato tantissimo dal dialogo continuo con la fondazione, con gli SPOC. Si dice padrone, oggi faccio più buono, però è chiaro che sin da subito noi al Ministero abbiamo pensato che non dovevamo metterci su un fronte contrapposto rispetto a chi stava facendo l'investimento, bisognava partecipare all'investimento, entrare dentro la comunità e insieme portare avanti l'operazione, condividendo soluzioni, individuando problemi, cercando di prevenirli piuttosto che risolverli a posteriori, e insistendo costantemente sul corretto avanzamento, sul rispetto degli obiettivi, sulla capacità di fare previsioni di spesa e di previsioni di attività attendibili e riscontrabili. Solo così, andando avanti insieme, si riesce ad arrivare in porto positivamente. Però poi giustamente è stato detto, dobbiamo essere consapevoli che non ci basta arrivare in porto. Noi dobbiamo chiudere bene questi investimenti, abbiamo 1 anno e mezzo di fronte in cui dobbiamo lavorare ancora moltissimo, molto di più di quanto possiamo aver lavorato fino adesso, ma quello che facciamo oggi, quello che facciamo oggi pomeriggio, quello che abbiamo fatto ieri mattina è già proiettato al futuro, è già una condizione, un tassello che ci serve per ragionare sul futuro, e quindi dobbiamo cominciare a capire le prospettive di una comunità di questo genere, le prospettive di una fondazione come quella di Restart, cercando anche di valorizzare i possibili collegamenti sia territoriali sia tecnologici con altri programmi, con altre esperienze. E solo questo partenariato ha reclutato circa 100 nuovi ricercatori, dando loro un'opportunità straordinaria, perché sono immersi nel sistema della ricerca, hanno contribuito come tutti gli altri programmi. Stiamo viaggiando su cifre di nuovi reclutamenti in circa 8.000 persone soltanto con questi interventi del PNRR. Siamo riusciti ad abbassare l'età media del sistema della ricerca pubblica, abbiamo alzato la presenza del genere femminile, anche in settori come questo, che magari sono un pochino più complessi da questo punto di vista, ma ci dobbiamo chiedere cosa facciamo di tutti questi talenti dopo. Questi finisce il PNRR, finiscono le cose del PNRR e non possiamo scoprirlo il 1° gennaio 2026 che le risorse poi sono finite. Noi dobbiamo oggi lavorare per costruire le prospettive e il futuro, e credere per esempio sul valore della collaborazione e dell'integrazione, perché finché ci sono i soldi pubblici si collabora facilmente. Dobbiamo riuscire a collaborare e a credere nel valore della collaborazione pubblico-privata anche il giorno in cui le risorse del PNRR saranno finite. Il rischio forte, dobbiamo saperlo, che l'ondata di queste risorse sia una specie di ubriacatura da cui poi ci si risveglia male. Se noi lavoriamo bene oggi, sia scientificamente sia dal punto di vista amministrativo, io lo dico e l'ho ripetuto anche nel corso di tutti gli audit che abbiamo fatto nel corso del mese di giugno, l'operazione PNRR ha questa caratteristica che tenta di mettere insieme il dettaglio del quotidiano con la prospettiva, con la proiezione futura. E noi dobbiamo sapere che anche quella piccola attività che facciamo, che sembra irrilevante, che sembra insignificante, caricare bene una spesa, rendicontare bene un pezzo di carta, fare bene un tipo di previsione, non è qualcosa che rimane lì fino a se stessa, è un adempimento, che seccatura, questi del Ministero ci chiedono i rendiconti 2 volte al mese, sono dei pazzi. È tutto funzionale al futuro, tutto quello che sappiamo fare oggi, che impariamo a fare oggi, ci servirà dopo e sarà l'eredità da cui poi si ripartirà dopo. E se noi, grazie a queste operazioni di PNRR, avremo imparato a lavorare diversamente, a ragionare diversamente, al di là dei contenuti scientifici pur validissimi dei progetti, ognuno, per carità, non sta a me parlare di questo. Io sono attento al fatto che l'opportunità di cambiamento che ci ha dato il PNRR sia sfruttata veramente, ed è un cambiamento che deve essere culturale, veramente mentale profondo. Se riusciamo a far questo, noi non torneremo più indietro, non vorremmo più ragionare come in passato, ma questo lo costruiamo quotidianamente, minuto per minuto, secondo per secondo, faticando, perché questa roba si fa soltanto con grandissima fatica, La facciamo insieme, noi non ci tiriamo mai indietro, siamo i primi a imporre di faticare, ma perché fatichiamo noi quotidianamente. Questa comunità ci sta dimostrando, in particolare la comunità di Restart, ci sta dimostrando, lo dico perché l'ho detto più volte, avete dimostrato di aver compreso determinati meccanismi e determinate metodologie prima di altri, forse meglio di altri, e non disperdete questo valore, potenziatelo. E soprattutto non siate mai soddisfatti di quello che state facendo. L'avete fatto bene, siete bravi, bene, ripartiamo per essere ancora più bravi. Come dicevo nel corso degli audit a tutti, a noi non ci interessa che siate bravi, a noi ci interessa che siate i migliori su tutto. Essere bravi sono buoni tutti, sono capaci tutti. Essere i migliori è una cosa diversa. Il PNR ci chiede di essere i migliori sul nostro campo e da tutti i punti di vista. Finché abbiamo una stilla di energia, noi la mettiamo a disposizione per questo obiettivo. Intanto vi ringrazio di nuovo e vi auguro una splendida giornata di lavoro qui a Catania. Qui si sta bene, freschi, fuori fa un caldo. Sì, vi auguro ancora buona giornata. Grazie.
Ora, proseguiamo con l'ultima parte dei saluti, però entriamo un po' nei contenuti. Io do la parola a Marco Rendina, che è di Astel. Con Astel Restart ha siglato un MOU di collaborazione su una serie di tematiche, perché, lo diceva prima dottor Cobis, la collaborazione significa anche poi avere impatto sul mondo delle imprese, e Astel come stagione di categoria rappresenta per noi il riferimento più importante per cercare di avere poi un rapporto diretto non soltanto con le aziende che fanno parte del consorzio, ma anche con l'associazione che le rappresenta tutte, che in qualche modo ci dà l'opportunità poi di mettere a terra le ricerche che facciamo. Marco, la parola a te. Grazie.
Buongiorno, grazie dell'invito, ringrazio il Rettore Priolo, ringrazio il Professor Palazzo, naturalmente il Presidente Blefari e il Professor Capone per l'invito. Io vengo qui per porgere il mio saluto a questa platea come rappresentante di Astel, l'associazione che nel sistema di Confindustria rappresenta tutte le imprese della filiera delle telecomunicazioni. Abbiamo una partnership strutturata con la Fondazione Restart, quindi è con grande piacere che prendo la parola oggi. Volevo farlo seguendo un filo che è trasversale a tutti gli argomenti. Ho visto che nel panel in queste 2 giornate si parlerà sostanzialmente di futuro, di cose immaginifiche, però ecco, un punto trasversale è quello delle competenze. Ok, allora, intanto c'è una presentazione, la presentazione rimarrà agli atti del convegno e del workshop, e pertanto non mi soffermerò chiaramente per ogni slide, ma solo su alcuni elementi essenziali. Il primo dei quali è quello di raccontare appunto che cos'è la filiera delle telecomunicazioni. Qui la vedete rappresentata secondo diciamo un'immagine che rende un po' tutte le sue componenti, ma sostanzialmente parliamo di 3 blocchi, no? Coloro che fanno le infrastrutture, gli operatori di telecomunicazione, naturalmente i servizi, che sono la parte più interessante perché è quella di sviluppo del settore delle telecomunicazioni. Anche qualche numero su Astel. Complessivamente 27 miliardi sono i ricavi degli operatori, circa 200.000 lavoratori. Questo numero comprende naturalmente tutto l'indotto, circa 100.000 sono quelli impiegati direttamente dalle imprese assistite. Direi di andare su questa slide che prova a riassumere sostanzialmente un intero processo che è in corso. Con le infrastrutture di telecomunicazione sono alla base, cioè le telecomunicazioni attraverso la rete di infrastrutture sono abilitatori di tutti i fenomeni di trasformazione digitale di cui si parlerà più ancora diffusamente, ma soprattutto si rivolgono poi al mondo dei servizi e investono sempre di più nei nuovi servizi digitali. Ma questo è solo per dare un inquadramento, ma il messaggio che per noi è importante è che solo la disponibilità di competenze in numero e qualità adeguate può consentire alla filiera di assolvere a questa missione e di completare e di coglierne tutte le opportunità. E allora, come siamo messi con l'occupazione della filiera? Allora, questi dati si fermano al 2022 perché ogni anno gli osservatori Digital Innovation del Politecnico di Milano predispongono un rapporto, quello del 2024, che quindi prenderà i dati del 2023, sarà presentato, e così ci facciamo anche un pochino di pubblicità a novembre nel nostro forum nazionale delle telecomunicazioni. Questi sono i dati del 2022, però si possono già cogliere alcune tendenze. Quindi chiaramente c'è una flessione, ma questo è un dato comune a tutti i principali paesi europei, forse con l'eccezione mi sembra della Spagna, quindi c'è una flessione. Non solo, ma poi abbiamo anche un problema di età anagrafica. È una filiera di persone non giovanissime. Questo naturalmente spinge le imprese a mettere in atto delle azioni per dotarsi, sia per diventare attrattive verso i giovani talenti. Prima si diceva investire nelle telecomunicazioni, investire nei giovani, certo, è esattamente quello che anche le imprese per prime della filiera delle telecomunicazioni devono fare, è proprio essere attrattive, ma bisogna anche pensare ai lavoratori che sono già impegnati all'interno della filiera e le loro competenze vanno adattate. Ed ecco quindi i 2 filoni che vedremo di azioni rivolte all'interno e verso l'esterno del nostro mondo industriale. Qui abbiamo interpellato le nostre direzioni del personale e abbiamo chiesto loro quali fossero le sfide principali che si attenevano. Perché ho voluto mettere questa slide? Perché voi vedete che riqualificazione delle persone, definizione di nuovi modelli di gestione e di sviluppo delle performance, e sviluppo di cultura competenze digitali, ma qui c'è un denominatore comune che è proprio quello di avere una forza lavoro sempre più skillata e sempre più ingaggiata su questi temi. Questi dati sono del 2022 e sono nelle prime posizioni, poi c'è anche l'engagement delle persone, che però è un dato comune, anche quando si paragona al totale mercato, si esce dal mondo delle telecomunicazioni, resta sempre un punto di grandissima importanza per il mondo delle imprese, soprattutto in un mercato fortemente competitivo come quello delle telecomunicazioni. A destra vedete quelle freccine gialle che abbiamo inserito, è perché non abbiamo ancora dei dati consolidati, ma delle tendenze sì. E allora vediamo che in realtà sembrano in flessione, ma quello che volevo mettere in evidenza è che è cresciuto nell'interesse delle nostre direzioni HR il tema della gestione delle riorganizzazioni aziendali. Questo forse è anche un tema legato a delle trasformazioni che sono sotto gli occhi di tutti e che stanno avvenendo e che incideranno profondamente sul nostro settore. Vado molto veloce, qui è un elenco delle professionalità, credo che nessuno dei presenti sia stupito di vedere cyber security, social media, web marketing, internet of things, big data e analytics, sia tra le, perché qui la domanda esatta che era stata fatta, vedete, per professionalità presenti è: sono già in numero presenti nella vostra organizzazione? E chiaramente ci sono. L'altra domanda è: prevedete di acquisirne nei prossimi 12 mesi? Poi nella sintesi è diventato professionalità ricercate. Quindi ce ne sono, ma ne vorremmo avere ancora di più. Dicevamo, e come? Quindi o andare sul mercato oppure facendo azioni di formazione verso le persone della filiera. In questo le imprese stanno investendo, l'avevamo chiesto di fare, ce l'ha fatto proprio il Politecnico di Milano, ha fatto un'indagine nel 2021 chiedendo alle imprese: ma proiettatevi 5 anni, adesso pensate chiedere oggi a un'impresa cosa farà fra 5 anni, chiederlo nel 2021, però sulla formazione ci hanno detto sì, noi formeremo sostanzialmente il 100% dei lavoratori che abbiamo in forza attraverso programmi soprattutto di upskilling e anche di reskilling, previsione che si è confermata pienamente a consuntivo. 6 giornate medie di formazione nel 2022, nel 2023 sono forse qualcosina di meno, ma questo perché chiaramente poi la formazione si arriva a un punto dove comincia anche a dare dei risultati. Diciamo che è anche un fatto come dire, fisiologico, anche positivo, significa che i processi che sono stati messi in corso e sono stati messi in campo hanno dato i loro risultati. La slide successiva la salto perché sostanzialmente è una ripetizione di quello che è stato detto prima, e qui invece guardiamo di più al mercato esterno, perché anche prima se ne parlava. Quindi 6.200 persone, secondo il rapporto Unioncamere Ampal, è il mismatch nelle materie STEM. Le materie STEM naturalmente nelle università sono le più importanti perché le competenze ICT, come abbiamo visto prima quando abbiamo guardato le competenze, sono quelle naturalmente più ricercate e quelle più ricercate in un'ottica di sviluppo. Questo dato del 75%, qui ritorniamo aver chiesto alle imprese quali erano, diciamo, i temi più importanti, rilevavano una difficoltà ad assumere il personale in 3 casi su 4 a causa della scarsità del mercato delle professionalità richieste. E diciamola tutta, anche perché sono anche molto contese, essendo scarse, quindi c'è anche un tema di contendibilità di queste risorse. L'ultimo punto che ho inserito è che io, come sono un rappresentante di associazione, allora è chiaro che le cose avvengono nelle imprese e le azioni più importanti in questi campi le fanno le imprese, ma anche le associazioni di rappresentanza giocano la loro partita. La nostra stessa adesione alla Fondazione Restart, la nostra stessa presenza oggi è a testimonianza di quanto io faccio lavoro e relazioni industriali. 20 anni fa non parlavamo di competenze, parlavamo soprattutto di contratto, parlavamo soprattutto di retribuzioni, che continua a essere un punto molto importante, ma oggi le competenze hanno scalato il tema, no, di partecipare e di fare sistema insieme alle istituzioni, di fare sistema con il mondo accademico. Sono poi le parole che abbiamo sentito oggi negli interventi che mi hanno preceduto, anche l'intervento del dottor Cobbis, ascoltavo nel MUR, che parlava di alleanza strategica, ma è esattamente questo quello che noi cerchiamo. Allora, qual è il contributo che un'associazione può fare? Perché non è più della singola impresa, ma di metterle insieme tutte. Abbiamo provato a fare una mappa abbiamo realizzato 8 anni fa la mappa dei ruoli e competenze. Che cosa significa? Provare a dare un linguaggio uniforme che abbiamo messo a disposizione proprio del mondo accademico, della Fondazione Restart, ma l'abbiamo messo a disposizione di tutti gli interlocutori, ed è anche uno strumento che può essere utile per le azioni di upskilling e reskilling, dove qui abbiamo provato proprio a condensare in 70 competenze professionali, questo lo chiamiamo alternativamente ruoli e competenze e ruoli, perché non siamo partiti dal ruolo come si fa ad esempio nei contratti collettivi e poi abbiamo descritto qual è la loro attività, ma abbiamo fatto il contrario, cioè siamo partiti, chiaramente il campo, ad esempio l'intelligenza artificiale, la metodologia di formazione, aula, blended, adesso quella che può essere, descrizione dei contenuti, ad esempio quali competenze deve avere, non so, questa persona deve avere competenze di programmazione ma al tempo stesso avere anche delle competenze linguistiche, ma che cosa ci aspettiamo che faccia? Beh, che renda accessibile, che renda comprensibile il linguaggio dell'intelligenza artificiale a chi la utilizza. E allora che cosa abbiamo? Il job attendere, il prompt engineer, che è un po' l'ultimo arrivato nell'aggiornamento 2024 di questa mappa delle competenze. Capisco che ho semplificato tantissimo, guardo, però dobbiamo avere uno strumento che sia, come dire, fruibile e intelligibile a una platea che non sempre però è formata di, come dire, di specialisti e di persone che sono dentro questo mondo pienamente. Dobbiamo parlare con tutti e allora abbiamo bisogno di strumenti che abbiano anche l'immediatezza. Questo è anche un po' il tempo della comunicazione, quindi anche in questi temi che vanno anche a rischio di qualche semplificazione. E qui va bene, qui ci andrei molto veloce, quello che facciamo perché che le aziende abbiano in campo collaborazioni, questo non devo certo raccontarlo a voi che venite da tutti i mondi, quello industriale e accademico. Quello che fa Astel come associazione chiaramente è un passo indietro provando a rappresentare tutti, quindi la mappatura ve l'ho già raccontato, Restart rientra chiaramente nelle partnership pubbliche e private perché partecipiamo a questo progetto. E quindi andiamo velocemente, ecco qui sono alcuni esempi ma a sorvolo comunque sono agli atti, per arrivare alla collaborazione che abbiamo siglato e formalizzato il 24 febbraio scorso con la Fondazione Restart per collaborare allo sviluppo e divulgazione di progetti di interesse comune per promuovere progressi nel settore delle telecomunicazioni. Lo abbiamo detto anche prima, anche questa mi sembra una parola che abbiamo già ascoltato nei precedenti interventi. Il primo progetto su cui stiamo collaborando è proprio quello della agire insieme per promuovere l'introduzione di corsi attinenti alle telecomunicazioni negli atenei. Molto importante su questo utilizzare un linguaggio comune che affiniamo insieme, è un progetto a cui partecipiamo sia noi come associazione sia naturalmente le nostre associate. Spero di non aver sforato per i tempi, l'ultima cosa che faccio è di augurare a tutti un buon lavoro, salutarvi. Grazie.
Grazie Marco.
Good morning. We'll switch to English also because we have our reviewers that are listening to us. So thank you for being here, especially to the Magnifico Rettore of Catania and to Dr. Kobis and to Sergio Palazzo that organized everything together with the people here. I also thank them for not only for being here, but also for their support, and especially for the point about the life after, what the life after the foundation, the first 3 years will be like. So I will present once again the Restart program, since we have many new partners. So, of course, I will maybe repeat things that are well known to the other people here. But, like I said, we have several new people, new colleagues here. So we started with 25, now 26 partners, because there has been a split of partners, with 12 universities, 11 companies, and 3 national research centers. Then, by means of the tool of the so-called cascade calls, of which we have 2 waves. The first one has been completed for a total amount of about 30 million euro. The second wave is in progress, and it's aimed especially to SMEs and startups and spin-offs. So I was saying, thanks to this first wave of cascade calls, other 36 companies, 1 foundation, and 30 universities joined the program through this tool. So we are now but exactly, right now, 93 partners. The original 26 plus 67. Of them, we have 42 public universities, 3 national research centers, and the primary operators, vendors, and technology providers in the sector of telecommunication in Italy. So we can claim that this program, we call it a program since it is a collection of projects. It's not only one project. We represent a significant portion of the Italian community. And this is both an honor but a responsibility, because this is fostering efficiencies, but it's also, let's say, a big hope of doing really something for our country. I always like to start with this slide, since our program includes 7 missions, of which the first one is the research, which of course is the most important. But I always say that, in my opinion, the other 6 are most important for this program, in the sense that research is something that we normally do, while these other missions, this we can do only by working together and thanks to the funding of this program. The missions are the labs. We are buying a lot of equipment, and we must try to use efficiently this money to leave something to our colleagues after the end of the program, and to have well-organized and big labs. We must not disperse the funding in small, let's say, tools and tasks. The third mission is about innovation and technology transfer. Then we have support to startup and spin-offs, education and training, which is most important, PhD programs, and communication, standardization, and open source solutions. Research is divided in 14 so-called structural projects, which are big projects, and 18 smaller focused projects. I'm very happy of what the projects are doing right now. In my opinion, we must now focus our efforts on the missions. This is very important. Also, the reviewers are of the same opinion. So I take the occasion to ask the colleagues that are taking care of these missions to improve their efforts on those tasks. I will not present the specific projects. We do not have the time. I'd like instead to present another area of work which we introduced during the project lifetime, which we call the grand challenges. And these are impact-stimulating transversal actions. So the idea here is that we try to go through the project, to collect all the good that we find in the project, and we try to bring those results to completion, to impact, and to an activity that can last over the years. As you can say, also the titles of these grand challenges are thought in a way as to be understandable also by the general public. Antonio, Professor Capone will talk about this challenge later on. So I will not say more about this. But this is another area that we believe it's very, very important for our program. From an administrative point of view, I translated RUP by using ChatGPT, and so we have this single person in charge of the project, which is also single. I would like also to thank our RUP in this, who is here. So we are about 30% of the total funding. We are doing well. I thank the RUP also because he authorized several categories of expenses which were not envisaged at the beginning. So I believe that now we have the tools to do what we like. We also built up an impressive team, an impressive support team, by using a funding of 3%, which partners graciously gave to us. And so we have already hired, in addition to Adele Del Bello, who is the managing director and program manager, who is, as you know, the only person that is allowed to be hired by the program. Mr. Kobis, but we try to circumvent this heavy limitation by hiring a lot of other people that are listed here. I'd like to mention them: Anastasia Di Lorenzo, Andrea Dao, Vittoria Kersic, Gianluca Massei, Alessandro Melino, Roberta Cristofari, Fabrizio Mariani, Angela Soldà, who are already working with us. But it's a precious help. It's not just administrative support, it's also technical support. We are hiring other people. We will have 25 of them, one for each partner. And all of them will be devoted to tasks that are hub and program-wise. So they're not only for the single partners. This is very important. We are very happy about that. Now, the last part of my talk is about the telecommunication sector. We are facing some evils that are there since several years that make our sector suffering, especially in the last year, which are an excessive cost competition among operators, an unfair competition with hyperscaler. Hyperscaler are the over-the-top, Google, Amazon, Facebook, and so on and so forth. The competition is unfair in terms of legislation and in terms of regulation. This is making the operator suffering, and this is putting at risk very much needed investments in the infrastructure. Spectrum costs. Many argue that spectrum has been paid too much, once again limiting investments in the infrastructure. Growing energy costs, but we must also recognize our own responsibilities. So I think that we have something that we must respond of, a certain lack of readiness to offer evolved services and innovation, which created empty spaces. Which are these empty spaces? You know the history of telecommunication, but if you look at the early days of the internet, we didn't implement, the operators didn't implement multicast, broadcast, service differentiation, IP mobility, enough addresses. This opened the door to new players. In my opinion, this is why new players entered the telecommunications market, because the telecommunication people didn't provide very much needed functionality. And they entered our house, let's say. Then this went on, because also content delivery networks, network services, cloud, internet exchange points, in-network processing. This has not been done by operators and by the telecommunication vendors. And once again, other people did it, and is doing that. So we now have hyperscalers, I mentioned that, tower companies, the very recent division of NetCo and ServCo of TIM. It's another consequence of this year-long trend. It's the fact that there is empty spaces and voids. And voids are filled. You see here low-pressure areas. You see, when there is a low pressure, the wind comes from the other direction. No? And so we got the hyperscaler. But the fact is that now they are not only providing functionality, they are also buying and building private links and networks, intercontinental, metro, and now in access network. They have proprietary protocols and algorithms, which has an impact on science, technology, standardization. There is a crisis of the standardization fora. The regulation is very old. It must be certainly improved and changed. It seems like it's 20 years ago, also the regulation. If you want to find some materials about that, there are some links there. And we have increasing signs of Google as a network operator. Off the records, Google is currently disappearing from internet exchange points. This is a very, very bad sign, which means that it will use their own network. And the last void to be filled is the one between the network and the application, which traditionally is not our work. But since we have been invaded by other people in our own house, then maybe we can try to fight back and go and do something somewhere else. This is also, in my opinion, the main reason why 5G is not as successful as it will be for sure in the future, and as it is right now in China, for instance. The gap between the network and the application. For instance, you have an hospital, you have a subway, you have the subway around, you put 5G, the connectivity in the subway, but if you don't provide the service, the slices, all that you need before the application, it's good. I'm not saying it's not good, but it's not enough. Think to a hospital. It's good to cover a hospital with 5G, but without the smart charts, without the doctors being connected, without the localization, it's not what 5G was meant to be. And this means that maybe we will lose to Wi-Fi if we do not act right now. I have a project proposal that is trying to do exactly that, to introduce a service microlayer to create this functionality. I do not have the time to present it right here. The message that I want to give is that low pressure means cyclone, hurricanes, tornado, rains, thunderstorms. So we must fill this void to go towards an anticyclone with a high pressure to enjoy clear skies and suns as we do in Catania and in Sicily in general. So, and I conclude, we have two very big strategic actions on top of everything. The first one is to expand the scope of the networking community and work towards this so-called service layer in terms of science, technology, but also standardization and regulations. And two small ideas are maybe, but maybe I will present later on, to charge data flow, forget about that. Important the fact that maybe operators would need a stronger support, and maybe we should think to an European company like Airbus. Maybe not everybody knows that Airbus has been created by the government, and now is a strong competitor of Boeing. So it's a world leader in terms of airplanes production. I believe that we are at a point that we might need something like that for the telecommunication. And the last strategic action is teaching, which is a controversial issue, but we certainly need a common degree name in all Italy, a common set of core topics, and then we can have a national advertising and support, which we can fund with Restart. So we must agree on a common degree name, on a common set of core topics, the community, all the community, and advertise it. This is very much needed. We lost 15 years, we lost the software revolution, we must not lose the master degree and the AI revolution, and we must fight back. I understand, like Dominique Moisy says, that the beginning of decadence is the most beautiful time for a civilization, but no one controls the speed of their decline. So we are fine. But this applies also more in general than the teaching in telecommunication. This applies maybe to let's say, our countries, our region. No? It's beautiful. The end of the Roman Empire was the most beautiful time of the Roman Empire. But then it ends. So I do not know if we can reverse these trends, but we should try. And this is also why the name Restart. But I want to conclude on a positive note. The internet value chain keeps on growing, 15% per year. So it's not a decline in terms of money, in terms of investment. It's that it's moving in other places, to other people. But the potential is there. And Restart is a great tool and a great opportunity to do that. Thank you.
Good morning, everybody. We are already quite behind the schedule, so I will try to shorten a little bit my presentation. My goal is that of presenting the program that we have for the workshop today and how we are going with the research activities in Restart. The message I got from the introductory talks today is that somehow, the good quality of the research that we are doing is given for granted. I'm not completely sure this is the right attitude that we have, because as we know, research is a complex thing. And like complex things, it has a real and imaginary part. We are working in the direction of making our research real, which means that with an impact on the telecommunication sector, which is the final goal of Restart, right? It's not so easy as it may appear, and even if we are good in doing research, as the numbers are showing, these are the main KPIs that we are providing to our international reviewers and the ministry for that we put in the program, and that we are monitoring continuously, showing that we are all above the targets that we gave at the beginning. This is not enough. We are trying to do more, because of course the point is trying to translate the research results that we are obtaining in something that can have an impact on our sector. And in general, the projects are doing well. We will see today the goal of the workshop in the middle of the program duration is that of looking inside our project and having an overview of the results that we are obtaining. We are conducting periodically audits to all the projects, and we can say that in general they are well on track. We have minor deviations with good counter actions that have been taken for tackling the deviations that we have. Most of the issues with recruiting have been basically fixed. And I can say also that what Nicola said with the partners that entered the program with the cascade calls, somehow they are providing a new wave of energy to our research activities, and this is extremely positive. Also, the level of collaboration among the partners is good. This can be seen from the joint publications, but also on many other activities that are less visible. And also, after a little bit of slow start, now the collaboration of the industrial partners is very good. We have now periodical meetings dedicated also to stimulating more the participation of industrial partners, because of course those that are in the program, including those that join in the program with the cascade calls, they are the fundamental partners that can exploit the research that we are conducting. And if you look inside the programs, inside the project, the results that they are obtaining, you can easily spot. And if you just look at the web pages that we have on the Restart Foundation website, we have listed project by project the main results that they are obtaining. If you take a look, you can see that even identifying the most important results is difficult, because there are many, but looking at those that the partners of the project are highlighting, it's interesting because you get an overview of the research that we are doing, and the quality of the research that have been obtained, with an interesting global picture that you can get. This global picture is something on which we are working, and we are working together also for creating this global picture of how the future of the technological part of telecommunication will look like, and this is actually one of the goals that we have in the second part of the program. Also, a number of exploitable results are already being obtained, and probably the number will increase in the second part, because of course typically, the first part is dedicated to some more explorative research. Nicola mentioned already the grand challenges. This is the instrument that we decided to adopt for stimulating cross-project research. Last time in the plenary meeting in Bologna, we announced some specific actions for having specific activities on the grand challenges. And I can tell you that we started with all, and we have now cross-project groups working on the grand challenges. We have appointed coordinators, one or more per grand challenge. All the projects are contributing to at least one, And all the grand challenges have several projects involved. This is interesting. Of course, not all the challenges have the same priority, but this is normal. In particular, we are giving priorities to those challenges that can stimulate the collaboration also with other research programs like ours, in particular at European level. As you know, we have a network of national initiatives at the European level with which we are collaborating and that can also help us in having an impact that goes beyond the national ecosystem of telecommunications. I just want to very briefly mention some of them. We are in particular for the collaboration with the other national initiatives. We have created two challenges. One is dedicated to the digital twins and the exposure of the network to multiple tenants. And the other part is on the orchestration of network resources and the platform for providing services. They are somehow linked together with the coordination of Riccardo Marini, Roberto Verdone, and Carla Fabiana Chiasserini. And the idea is that of putting together also the experimental tools that have been developed, that are being developed in the research projects in order to create a collaboration on top of a concrete tool that can stimulate also the collaboration and with the industry and the potential impact of the activities that we are doing. But there are others on enabling technologies, for example, on artificial intelligence and how this can also change the way we transmit information in the network. We also have very important, we don't have to forget the importance of the basic technologies that we use. So we have on radio technologies, on propagation technologies, and on optical technologies and integrated optical technologies with a number of initiatives in this direction. But also, we know very well that telecommunications are not just a general purpose tool. They change depending on the application. So we also have a number of application domain-specific initiatives, for example, on dedicated on mobility, like the workshop that have been held yesterday, on the media part, which is fundamental as the application domain, and on extreme environments and networks working in these extreme environments. The last message is on this global vision that I mentioned. We are working in the direction not only of trying to figure out how the future will look like from a technological point of view, but also for the importance that it has on the economic point of view and the ecosystem and value chain. We have created a group working in this direction with a specific initiative in collaboration also with Astel for creating this common vision. We already published a white paper, a first version of the white paper that analyzed this future vision, which is techno-economical. But we are now asking for the collaboration of the people in Restart to show how things can create this coherent and common vision of the future. On this specific theme, but also on others, we will organize specific workshops. We don't have the time in a plenary workshop to go in deep and analyze this and also have collaboration from you. So we will ask you to participate to other thematic workshops in the second part of the program, because we believe that the collaboration, in particular in person, is fundamental. This is the program, very, very busy, so I will also ask all the speakers to stay on time on the schedule like we didn't, unfortunately, but I hope that you will do better than us. Let me also say that we will also have a poster session in parallel in the common area, and we will also award the best posters like we did in Bologna. All the attendees can vote for the best posters. So I stimulate you to go and talk to the people presenting the posters and vote for your preferred poster. With some rules, you cannot vote for posters authored by authors of your organization, just to stimulate a little bit of interaction with others and looking at what the other did. and also for stimulating the discussions, informal discussions outside this room. We will also award this time, in the middle of the project, the first best contributions that we have. So we had some submissions, and we will award the best scientific contributions and the best impact contributions. We have created a short list, and we have created an award committee that will work today and tomorrow for selecting the best contributions. They will give very brief pitches, 5 minutes, today at the end of the program and tomorrow at 8:30. Probably this is one of the most interesting part of the workshop, so I encourage you to stay until the end today and to come very early tomorrow morning at 8:30 to listen to these speeches. I stop here. I thank you all for coming in this workshop today. Thank you. Great. So it's now time to start with the program. So I call here Davide Dardari for the first session. Davide, the floor is yours.
Good morning to everybody. So today I'm talking about smart radio propagation, smart propagation environments. I'm Davide Dardari from the University of Bologna. So this is also one of the great challenges that Antonio mentioned before. What I'm going to do is to give you a very brief overview about the challenges, but also the opportunities behind the smart propagation environments, and also a few spots on the main research results that we obtained within the Restart program on this topic. So we all know that moving from 5G to 6G, there are very stringent KPIs in terms of massive capacity, low latency, security, high reliability, and also the exploitation of high-frequency bands, millimeter waves, terahertz, and so on and so forth. So obviously the typical trend to approach such KPIs is to increase the number of base stations, antennas, so massive MIMO, for instance, and also to delegate the computation toward the edge, so extreme virtualization of the hardware functions. But at the same time, you have several critical points. One is the propagation. So this is the negative role played by the environment, so the propagation. And also the need for massive local computation has some drawbacks in terms of computation time, so latency, but in particular power consumption. And then one of the main issues are how to approach the performance, the KPIs, at the same time have sustainable networks. So we need for some paradigm changes. One of them is the smart radio environments, which is a paradigm change at the physical layer mainly, not only. So today, the approach we follow to design a wireless communication network is to estimate something about the environment, propagation environment, some parameters, and then try to optimize the communication network according to the environment. So the communication network adapts to the environment. So instead, in smart radio environments, the environment becomes part of the optimization process, so enter in the loop the optimization process by deploying specific electromagnetic devices, possibly low-cost, low-energy consumption devices, such as intelligent metal surfaces, but not only. But moreover, we can also think about delegating some signal processing functionality directly at the electromagnetic level, so in the environment, in order to reduce the power consumption, the energy consumption, and the latency, and so on. So we are moving from software-defined radio to software-defined environments. So what are the main, let's say, opportunities and trends within this topic? I'll just list some. Okay? So obviously we need new devices, new metamaterial, new technologies, and also novel tools for the design of such electromagnetic devices. a very nice topic, a very, let's say, hot topic today is the communication in a sensing near field condition. I will say something later. Also, as I mentioned before, the possibility to perform computing directly at electromagnetic level, so wave-based computing. And then, using these ingredients, we can think about improving the performance of existing applications, but also new applications such as integrated sensing communication, radio SLAM, just to mention some. But all this would be possible only if we tighten the interaction between two different worlds that, so for the time being, have been, let's say, a little bit decoupled, we say. So the electromagnetic theory world and the communication information theory world. So this is mandatory, otherwise we cannot, let's say, address such opportunities. And this is the one of the, I would say, the main good results that we are obtaining within the Restart project, in particular within some structural and focus project in Restart, that is putting together communities that before, let's say, never or really collaborated. And then I'm mentioning the two projects that are, say, closely related to smart radio environments. One is the project Smart Radio Environments, Professor Riccio and myself, and also the focus project MOS, Professor Degli Esposti. So let me now show what are the three key pillars of these projects. One is the design methods for electromagnetic, novel electromagnetic devices. Then we have the development of novel technology components. And also the signal processing of information theory based algorithms that can take advantage of these new technology components to realize new functionalities or improve existing functionalities. So these are the three pillars. So let me show briefly some key results we obtained within these two projects about these three pillars. So regarding new technologies, one nice new technology is that related to smart skin. So smart skin, we can think about a sort of electromagnetic sheet. You can deploy, for instance, bending a light pole in order to modify the propagation and, for instance, extend the coverage at a very, very low cost in a no-line of sight condition. An extension of smart skin is the metaprisms. So this is a new idea. Basically, these are metaprisms, or passive devices that are selective in frequency in a particular way, such as we can decide how the signal is reflected by playing with the spectral characteristic of this signal. So we can let's say, cover a non-line of sight area without configuring the surface, so without any interaction with the metasurface. So the metasurface can be passive, so no energy consumption at all. Other technologies are, for instance, reconfigurable intelligent surfaces working at a terahertz. So terahertz is basically the last frontier of the radio spectrum before the optics. And so everything at terahertz is very complicated, as you can imagine. And then the idea is to use liquid crystal technology to realize low cost and effective reconfigurable intelligent surfaces at these frequencies. A completely different technology to realize both RIS and antennas is that based on plasma discharges. Actually, this is not a low energy consumption technology, but has some advantage in terms of, for instance, transparency, because when you switch off the antenna, so you cannot see anymore the antenna, so the antenna becomes completely transparent. This is one possible, let's say, advantage. Instead, if you want to get extremely low energy, high energy efficient devices, another technology under study is the antenna arrays based on nanometric ferroelectric layers. that have a very nice property to have a very extremely low power consumption. So we can think about antenna arrays exploiting energy harvesting. So basically based on the energy that is already present in the environment to work to address, for instance, the beamforming and so on. I mentioned before near-field communication sensing. Why this is becoming very important? Because let me show this plot. So in this plot we see the Fraunhofer distance as a function of the frequency for different antenna sizes. So as you know, the Fraunhofer distance is a conventional distance. Beyond that, we can think about plane wave propagation. And this is typically the assumption that most of the models in people working in signal processing, information theory make, because while we work in, if we work in the low frequencies, so the Fraunhofer distance is very short, so it's a few meters, for instance. And then this assumption, the far field assumption, is good. But if we increase the frequency, millimeter wave, terahertz, and we, thanks to the previous technology, we are able to realize electrically large antennas, so that the Fraunhofer distance become 10 meters, 100 meters. So it is very likely that in most of the cases, the users, for instance, think about communication with users, are working in the near field regions, so where the propagation is no longer, let's say, considered to be almost plane, but is spherical. And then, from one hand, this means many of the models we are, people like me, I'm a signal processing guy, are using fail, so we have to change the model. But at the same time, we have new opportunities because a spherical wave carries more information from the communication point of view, but also from the localization point of view. So we can exploit such richness of information that we don't have with planar wave. But we need new design tools, new theories, and so on. Okay, let me skip some figures. Another important result we got in this project is asking what are the theoretical fundamental limits in near-field communication when we are also in the presence of a risk, for instance, to cover no line-of-sight condition. So what we got is a theoretical fundamental limit telling us what is the best, the optimal configuration of the risk in order to maximize the capacity. Well, one could think, okay, this is not just an academic result. No, this is not only academic result, because having in mind what is the horizon, so the theoretical limits, then we know what is, we can use this as a benchmark when we design practical systems. So we can see how far we are from the maximum we can get. Okay? And the same has been done not only for communication, but also for localization. So what is the best, the optimal risk configuration in order to provide the best localization tracking. There are also some other results in terms of processing algorithms. I will not insist on this because there will be a talk after me about this topic, so to save time, I will skip this. Then wave-based computing. So, you know, if we perform all the signal processing at the digital level, so we need a lot of analog to digital converters, a lot of RF chain, we need power, we need energy, and so on and so forth. So what about to delegate part of the processing directly at the physical layer, at the electromagnetic level? For instance, using computing metamaterials, or stack intelligent surfaces, or dynamic scattering arrays. For instance, dynamic scattering arrays is you can think about a few active antenna elements connected to RF chain, a few RF chain, and a cloud immersed in a cloud of programmable scatterers, so that by configuring properly in these scatterers, we can at the same time radiate a signal, but also let's say process the electromagnetic wave, so perform some processing over the air, actually. So for instance, we can perform simple beamforming, but we can perform precoding in MIMO system, and so on and so forth, with basically almost zero power consumption. So instead of making this in digital, we can make it a physical layer. Another technology investigated is the self-conjugated metasurfaces. But the idea is the following, so suppose that we want to establish a MIMO link. So what is the main problem MIMO link? Is that we want to perform a beamforming at both sides. So that takes time, latency, okay? What about doing that using a self-conjugated metasurface? So we have an extremely low capacity sensor, basically no digital say, processing. And this metasurface performs a conjugation operation. So by a proper, let's say, scheme at the base station, it is possible to avoid channel state information. We can, at the same time, track the beam and communicate without any, let's say, dedicated signal processing at the sensor side. So this is another approach. I mentioned a new application briefly. For instance, using the metaprism, we can see around an obstacle, so we can communicate or localize the user around the obstacle, so by using just one access point. And so instead of deploying several access points, we can just deploy a passive metaprism and obtain more or less the same results at a lower cost, lower energy consumption. Or another application example is radius LAM, so simultaneous localization mapping. So this is the world's first experimental validation of the radius LAM at Earth, so exploiting the imaging capability of Earth. And then finally, new design methods and tools. I will not insist on this because there will be another talk dedicated on that, but obviously these are very, very important. And I will conclude with the activity of the focus project MOS about one result of this project, which is the development of a macroscopic model for scattering for ray tracing implementation. And this model has been recently adopted in the commercial ray tracing tool by NVIDIA, Sionna. So this is, I think, is one good let's say, outcome of the project. This project also foreseen a sort of celebration demo at the Guglielmo Marconi Villa by replicating the famous Guglielmo Marconi experiment at the Villa Grifone, but using new technology, so metasurface and so on. So since I mentioned Marconi, since this year we are celebrating the 150 years of Marconi born, so I cannot conclude before citing Guglielmo Marconi, so never put limitation wireless, and this is an inspiration for us. This is what we are trying to do, so not to limit our imagination on wireless. Okay, thank you.
You hear me? Yes. Questions for Davide? We will try to, this is a recommendation for all the speakers, save a few minutes after each presentation for questions from the audience. Let me start with a question on, I think one of the most interesting in the research direction is that of the analog processing, considering these metasurfaces and metamaterials. What are from the implementation point of view, right? How far we are from real implementation, what are the challenges for making this real in a system that, of course, has some constraints in terms of exactly the type of processing you do, how precise you are, and so on.
Yes, I would say that for the time being, the research is mainly, let's say, related to simulation. So the modeling, in my opinion, is still, let's say, quite at a low level. It doesn't take into account some peculiarity of the structure. So there are very, very few prototypes for this in the world. So we hope to have some within the project, but for the time being, we are, let's say, at a very at tier 1, we say.
Thank you, Davide. Other questions? No? Okay, thank you. So we can move to the next speaker. Again, the session was organized by Davide, so the next speaker is Francesco Verde from the University of Naples, Federico II.
Good morning. Thank you for the introduction. In this talk, we will see why the rate of reconfigurability of digital coding metasurfaces is important in the wireless communication from a signal processing point of view. A digital coding metasurface is essentially a metasurface which is reconfigurable in the sense that the electromagnetic property of the illuminating wave can be changed in amplitude, phase, frequency, or polarization. In the wireless communication community, digital coding metasurfaces are referred to as RIS. And the intelligence of RIS is due to the fact that they are able to perform transformations that are not possible by nature, and most important, that the property of the metasurface can be configured based on network condition and on the information to be transmitted. An RIS is essentially composed of a certain number of unit cells, which are referred to as meta-atoms. Meta-atoms can be controlled by using timing circuits by means of biasing line. A typical timing circuit is composed of diodes, which can switch between two states on and off. And the reflection response of each meta-atoms can be changed by controlling the voltage of the biasing line. An RIS can be modulated both in space and time. Space modulation is obtained by implementing space gradient discontinuities along the surface, and time gradient phase discontinuities leads to time modulation of the reflection response of the metasurface. For a space-time RIS, the reflection response of the meta-atom can be written as a linear modulation over a given observation interval. The observation interval is divided into m subslots. Each subslot has a duration Tr, and the path shaping filter in its simplest form can be a rectangular window of duration Tr. The values of the reflection response in each subslot belongs to a discrete set which depends on the number of bits used to control the metasurface. What is the rate of reconfigurability? Okay, in our model, the rate of reconfigurability is given by the inverse of Tr. Okay, so 1 on Tr is the reconfigurability rate of the RIS. And such a reconfigurability rate depends on the bandwidth of the signal illuminating the RIS and depends on the task of the RIS. Okay? There are two potential tasks of interest for an RIS. In the former one, the RIS is used as a network booster. So in this case, the role of the RIS is just to improve the performance between an infrastructure transmitter and the users. And the second one, the RIS is used as an Internet IoT metasurface. In this case, the role of the metasurface is also to transfer information collected locally. Okay? Let us see how the rate 1 on Tr is related to the bandwidth of the signal. Let us assume a typical narrowband transmitted communication signals where the bandwidth is much smaller than the carrier frequency. In this case, from a physical point of view, from a signal point of view, we need accurate models of the reflection response of the metasurface, and accurate models are available only if the adiabatic feeding opposite condition is satisfied. The adiabatic condition says that the rate of reconfigurability has to be much smaller than the carrier frequency of the illuminated signal. This is a condition which is fulfilled in many cases of practical interest. And so we assume that this is fulfilled from now on. let us consider the first task as a network booster. As just to streamline ideas, let's consider the case of a typical multi-user downlink scenario, where we have an infrastructure transmitter that has to transmit information to capital K users, and the space-time RIS in this case is used to improve the performance between the communication performance between the transmitter and the users. Okay. What is the term of comparison in this case? The term of comparison in this case from the configurable rate is the Doppler channel spectrum, okay, which is inversely related to the channel coherence time. The channel coherence time is the time over which we can assume that the physical channel is essentially time invariant. Okay? There are two relevant cases. The first one is when the rate of reconfigurability is equal to the inverse of the coherence channel time, and the case when the rate of reconfigurability is greater than 1 on TC. Let us see the first case. In the first case, the rate of reconfigurability is equal to 1 on TC. This means that the response of the RIS is fixed over each channel coherence time. In our model, this means that M is equal to 1, so the observation interval is the coherence time of the channel, and the response of the metasurface is fixed. This is the case considered in almost all the papers dealing with RIS in downlink scenario. In this case, we see that we say that the RIS is slowly time varying. Okay, so if the RIS changes the response from one coherence time to another, we refer to as a slowly time varying RIS. Let us consider the case when the rate of reconfigurability is greater than 1 on TC. In this case, the channel seen by each user can be modeled as a linear time varying channel. Okay, so in this case, we have that the response of the RIS is introducing time variation within the coherence time of the channel. Okay. This time variation can be used as an additional degree of freedom to improve the communication. There are two possible improvements that can be observed in the second case. In the second case, we say that the RIS is rapidly time varying, and this time variation can be used to lower the signal overhead to optimize the system. Because typically, to optimize the system with an RIS, we need the full channel state information to transmitter. This means that the transmitter has to know all the channel included in the network. With a rapidly time varying metasurface, we can randomize the response of the metasurfaces in both space and time, introducing random variation of the channel, and this random variation of the channel can be used to gain multi-user diversity effect by using a lower signal overhead, by using partial channel state information to transmit. Another important consequence of rapidly time varying metasurfaces is the fact that they ensure a better fairness index. Let us consider the results of a simulation, numerical simulation, Monte Carlo simulation. We have considered a carrier frequency equal to 1.0 GHz, the bandwidth is 5 MHz, and the coherence time of the channel is 50 milliseconds. We have 2,500 time slots for each channel time coherence time. In this case, we have simulated the performance of a slowly time varying metasurface, STV. Opt means that full channel state information has been used at the transmitter, and we have simulated different versions of the rapidly time varying metasurfaces with and without proportional file scheduling in the allocation scheme of the resources. As you can see, if we consider, for instance, the yellow line, we have that a randomized rapidly time varying metasurfaces is able to exploit multi-user diversity gain, because as we can see, the sum of the rate of all users in the network improves as the number of users increases. On the other hand, if we look to the right of the right-hand figure, we have a better fairness index with respect to the case where slowly time-varying metasurfaces. The fair index, when the fair index is equal to 1, we have a completely fair system. When the fair index goes to 0, we have an unfair system. The same performance indicators are here reported as a function of the number of meta-atoms. And it is interesting to observe that, especially if we look at the red curve, that as the number of meta-atoms increases, the red curve, which is the rapidly time-varying metasurfaces with proportional fair scattering, allow a 100% fairness approaching the curve of the optimal case when we have full channel state information. Let us see the second case, the second task, okay? When the metasurface is used as an IoT metasurface. In this case, the situation is completely different, okay? So we have an IoT metasurface that transmits information to a secondary receiver by reflecting and modulating the signal transmitted by a primary system. The primary transmitter wishes to transmit information to the secondary receiver. Note that in this case, the primary receiver receives not only the signal transmitted by the primary transmitter, but also the deflection signal by the metasurface, okay, which contain information. On the other hand, the secondary receiver receives also the signal transmitted by the primary transmitter, which is interference because it's uncorrelated with respect to the signal, the data, information data transmitted by the metasurface. In this case, assuming that the primary system is a multi-carrier signal, an OFDM signal, which is used in 5G, 4G, and 5G communication system, and assuming that the current time is much greater than the OFDM symbol rate, symbol interval, we can, in this case, the term of comparison is not the channel current time, but the term of comparison is the OFDM symbol rate for the reconfigurable rate of the metasurface. And the cases are two. The first one is when the reconfigurable rate is equal or smaller than the OFDM symbol rate, and the case when the rate of reconfigurability is greater than the OFDM symbol rate. Let us see what the case of when the rate of reconfigurability is equal to 1 on TS, the OFDM symbol rate. In this case, we have that the metasurface transmits one symbol information symbol for each OFDM symbol of the primary system. So the channel which is seen by the receiver is changing from one OFDM symbol to another. This is not a problem for the primary system because typically the processing of the OFDM system is carried out on a symbol by symbol basis. But so in this case, if we see the results of a simulation, we have here simulated the system with two antennas at the primary transmitters, an OFDM system with 32 subcarriers, 20 megahertz of bandwidth, and this is the performance of the primary system as a function of the channel, of the variance of the reflection channel, okay? In the case when we have a metasurface, in the case without an IoT metasurface. As we can see, as the variance of the reflection channel increases, we have a performance gain of the primary system. So we are able to transmit information by means of IoT metasurface, and at the same time, we are able to improve the performance of the primary system. Let us see the bit error rate of the secondary system. In this case, is reported as a function of the channel variances of the direct reflection channel. As we can see, if we fix the variance of direct channel, we have that the performance of the secondary system improves as the variance of the reflection channel increases. Okay. On the other hand, if we fix the variance of the reflection channel, we see that as the variance of direct channel increases, the performance gets worse because this is due to the direct interference by the primary system. Just a few words about the last case, when the rate of reconfigurability is greater than the OFDM baud rate. In this case, we have an ultra-fast time varying RIS. Okay? So we are introducing time variation within the OFDM symbol. From one point of view, this is a problem for the primary system because time variation within the OFDM symbol complicates the modulation of the primary signal. The good news is that such a time variation can be used to reduce the effect of direct link interference. This is a trade-off that is currently under investigation. This is a short list of reference or main reference regarding to such works. Thank you very much.
Thank you. Time for one quick question to Francesco. Anyone? Of course, you will see today, and tomorrow, there will be presentations, high level and some more, research specific like this one. Of course, this is on purpose for giving you an overview of, the different activities that, of course, are on a broad range of topics. Let me ask you, Francesco, one question which is high level a little bit. One of the challenges of using RIS is that of using them in environments where you have multiple players that can use them because you have multiple networks, multiple operators. How this scenario can change the fundamental problems of designing RIS that can be controlled by multiple parties?
But I think that this is a very crucial point in smart radio environments, and I think that this is a problem that can be solved by network level instead of by a physical layer point of view. Okay, so I don't know exactly what is the solution. It's a use that is currently under investigation.
Thank you. Of course, this is one of the aspects that when we try to create cross-project activities and trying to see also the potential applications of what we do in the different projects. It's important to investigate because, of course, some of the practical issues in the implementation then can also drive the research in other directions or maybe simulate new ways of using the same instruments. So thank you again. So the last presentation for this session is from Giuseppe Vecchi, Politecnico di Torino.
Good morning, everybody. I'll try to keep this short. Maybe at a difference to the previous presentation, this is aimed at sort of giving the flavor of what's going on in this specific field. And it's more, a certain sort of more akin to the style of a presentation of our worthy coordinator, David, in the first one. First of all, acknowledging that I'm trying to relate about work done by different units, and it's one of the interesting part of the story. The focus of this thing is on passive electromagnetic skins. Passive, although we call them smart, you can call them dumb. Okay, they don't do anything, but that's their value. They are thin, they are cost-effective, and you can place them basically taking advantage of the existing environment and making it better, working together with the environment. This can be done in different ways. You can use of things. Okay, let me just. You can think of the usual thing. You have a blind zone, and then you put something that covers that in urban scenarios, big problems. You can have it indoor, we use it, and something which is emerging more and more over the years. It's over the actually months. It's indoor to outdoor, outdoor to indoor through windows, something which is transparent in the optical level. Then, apparently can't move on. Okay, all right. So these are the advantages of the thing, and foremost, you don't need any power supply. You don't need any other thing. You don't need any activity. They are smart because they are there. That's the advantage of this thing. Of course, you can do anything with this. Then the idea was trying to give a presentation of how we do these things. keeping it as high level as possible, so in order to not going very much into the detail, both people in my fields, we call them EM people, and the communication people, we all both love math, but they are different math, so I'll try to keep out of that and try to go into what actually were general ideas, which are actually common. So when you do a design, the first thing you want to do is the magic wand. If you have a magic wand, what do you want to do? Now, answering that question is probably the hardest part of the story. And answering this question has been one of the most exciting things in this project, because you need to talk to other people. And so I've been using the same scheme that David has been using between the two guys. I won't mention them. I'm just saying that the one on the right is not Karl Marx. And there is a story about that, but I'll tell you in the coffee break. So anyway, so the idea is the specification must come from the physical layer, right? And drafting board, meaning you're trying to do new things. And once you get to talk about fields, you're basically almost there, right? So you only have a problem to solve. Something which I think is very interesting is the one that David has mentioned, the meta prism. The meta prism is an example in which you are operating at different levels. I mean, it's basically a meta prism, OFDM, and it's EM at the same time. So that's one of the things. The other thing is that intimately, the specification are like Musk type. I want to special. You want to get something bigger here, lower there, this kind of thing. And once you get to that point, everything is field manipulation. Now, let me go to the bottom line. What I'm saying here is essentially trivia. But the trivia are like the magic wand thing. Once you understand that, this guide, the way you have to proceed. Okay. So first of all, how does it work? You got no EM scheme, then you get the field that you have, which usually you don't like. Then you insert it, and then you get something different, which is better. That explains a number of things that are along the way. And then wave propagation physics takes you to the surface and out of the surface everywhere. Okay, so, and I have some examples there just in figures. Okay, so what are the issues? Well, this thing is large, electrically large in wavelength. There's got a lot of little things that are actually populating the things, and these are the things that do the work. These things are called unit cells. They can be very small, and then you call them meta-atoms, kind of hyper. And then these kind of things are, then the overall thing is called metasurface by EM people. When you have resonance size, like half a wavelength, you call them with a different name, but it's pretty much the same thing. So the simulation of this thing, it's already a big problem. Okay, most of the commercial software will not do it for large surfaces. So at this point, you're asking, how am I going to do the design? Well, it is an essentially it's an optimization. What else is not an optimization in the word? So the first thing is that the direct approach, which means at each time you compute the cost function, you solve Maxwell equation for that thing, it's out of the job. So you need to go to some other better way. The easiest way is essentially going into the global optimization. You call them meta-heuristics, now machine learning. And that means that you need to get a reduced set of parameters. I mean, you can't do the whole thing, but you can do. So that's a smart part where you have to figure out how to simplify the problem. Something interesting that will come again, it's the idea of localization, homogenization. You got your little things. Instead of looking at the little things, you look at the field that they have around at a higher level, more or less wavelength level, and then that averaging, that homogenization is called local impedance boundary condition. You relate the two electric and magnetic fields by that kind of thing. In all cases, that means that you know what you're looking for. Okay, if you start point blank, you never get anywhere. Something which is evolving, and it's something new, and it's very interesting, that DM design can also be analytic based and deterministic. In some other fields, this is called inverse design, just to talk about names. And the idea is that you don't want to compute the solution to the problem for a candidate solution each time you run a cost function. And unfortunately, the problem by itself is non-convex. I'll say a few words about two techniques that are being developed within this project. One is the optimal synthesis using matrix, scattering matrices of the unit cell, and the other one is the current-based, current anomaly synthesis. Now, what is this the optimal synthesis using scattering matrices? In some simple situation, you can think of any one of these things, and then you consider, what is scattering matrix? Something comes in, and everything that comes out. And then you try to design that, and from that, then you recover the shape of the thing. There is a very mathematical part of the formulation in both, which I will absolutely not even touch on. But the idea is that by making the problem optimal, you can actually get to finding the properties of the surface field, and from these then getting the shape of these things using this scattering matrix approach. Very powerful. It doesn't need to know the layout. At present, 2D, you need to start somewhere. The other one, it's absolutely non-intuitive. You try to, the objective of your design is the final solution for the field. And from that, you recover all the rest. How you do it? Well, the key part is that you need to enforce that the surface field is realizable, is constrained by being physically realizable. And these are some examples of what you can do. And eventually, just a few words about what David has already mentioned about the joint project with the propagation part. You need to have fast propagation models based on the old concept of rays in a very innovative manner. And these are some of the things being done for doing this. And let me spend the last few minutes to give some examples. Now, first of all, we always think of planar surfaces. Now, planar surfaces might not be the right way of going around. For example, if you want to use the poles, you have already something which is curved, and that might be easily available at that point. So why not using curved things? And it turns out that they can work very well. This is an example of recovering, I think this was in Florence, a region where he had a blind spot, and by using this curved structure, you get a very good recovering of the structure of the blind spot. And then indoor scenarios, again, you can use these planar things, and something which is interesting from outdoor to indoor is that there is a chance of doing these things in a different manner. Most of the time you think of, you have a reflecting surface like a metal, and then you might use like printed circuit board or printed paper, and you put it there. Well, when you try to do indoor to outdoor, a very interesting thing is using windows. Now, windows obviously you do not want to be totally blind, right? So you want to have something which is optically transparent. So there is the chance of doing it with something really optically transparent, and that's very exciting because you can get inside without obstructing actually the windows. All right, and then pretty much, so other things like this. And these are just some examples of the way you can use all these methods to get there. And by these, I think I almost managed to get within the 10 minutes that I was asked to stay in. Thank you very much for staying with me so far.
Thank you, Giuseppe. Questions for Giuseppe? No one? Let me ask you this question. Of course, you mentioned, all the different challenges that you have in the design of these surfaces and how they can interact, Of course, since they are passive, the optimization must be tailored to the specific needs that you have, which means a specific system on specific frequencies and so on. But then they stay there. They stay there also for other systems. They stay there also for other frequencies. Of course, if they are tiny, of course, you can just use for the system you design them for. But in case they are large, typically they somehow modify the propagation also for, in general, all the spectrum and all the system, including those that you didn't consider in the design. how can this change the way we think to the environments and propagation environments?
That's a very interesting part, and actually, in the first place, this touches upon the problem of regulations, right? Whenever you put something, somewhere which is not a public building, and then you have other problems, then you need to get all the regulatory things that goes with that. One of the advantages of this thing is that they can be very cheap. Something like disposable. Just forget the blood thing and take it and scrape it away. I'm going the hard way. But there are other ways of looking at the thing, and you could think of replacing. You could think of basically having the authorization for just making small changes of the thing in an incremental manner, so that at least they do not go in the way of what you're doing. But one of the main idea about this thing is that they are something which is disposable, right? So that you can replace them. And they are not intrusive. That's one of, for example, one idea. You just put it on the pole, then you go back. Nobody even noticed that you're replacing the thing when you're, So if you have to put it on the window of somebody, well, that's a different story. But I think since we are going into the environment, we cannot avoid this, in quote, legal part. We are actually touching the environment somehow. And that's the question that we need to answer at a higher level.
Thank you.
Thank you.
Thank you again. So now we have the break outside. We will resume the session at 11:40 sharp. So please be here at 11:40 sharp. Anyhow, in any case, we will start at 11:40, right? So the next session is high frequency networks and systems. We will have 2 keynote speeches by Ernesto Limiti and Umberto Spagnolini, and 2 talks by Alessandro Fonte, and Miriam Vitiello. This is, of course, one of the main areas in which we are trying to have cross-project collaborations, and this is the reason why we have 2 speeches from 2 of the projects that are actually working together for trying to create some synergies among the activities that are done, in particular in this case, on radio technologies for high frequencies. So the first speaker is Ernesto Limiti, University of Rome, Tor Vergata. Ernesto, the floor is yours. Thanks.
Thank you, Antonio. And this speech will be slightly different from the previous one, since it's given towards, let's say, the physical layer. So, above all, speaking about electronics, and in particular the front-end electronics that is moving evidently towards the sub-terahertz range. This is the outline of the presentation. First of all, just the motivation, some drives. They are quite important to understand why we are going to access this technology and how we are going to access these technologies. Then just an overview of what is going on at transistor level, at amplifier level, both of the low noise and the high power, and at the module level. Then some game changer, let me say, that are more and more adopted in this field. So the adoption of active antenna array concept, more and more, and the new drive, quite important one, is the heterogeneous integration of technologies. So I want to start from a project that I've been involved in that is UltraWave. It's dated back 2017, and the title was Ultra Capacity Wireless Layer Beyond 100 GHz. The very peculiar thing is that some of the link were thought to be implemented through TWTs, so no integrated electronics, but even in that case, we were thinking about D-band transmission hub and access point, and also a transport layer at G-band, so up to 300 gigahertz. So we are trying to use 2 bandwidths that were quite innovative at that point, but now are going to be more and more attractive even for actual 5G and 6G. Hopefully, for the backhaul. This is just an idea of what is the D-band transmission hub and D-band terminal thought. And as you may see, one of the key components was a TWT, absolutely. But if you look at the various components that are within, both photonic and mimic components were synced in the system. So just a few ideas of what has been realized. So you will see many chips over there. So down converter mixer and an up converter mixer realized within the project. So there are no off-the-shelf components here. So things have been designed and realized within the consortium. Some of them by us. And also a D-band medium power amplifier integrated within the same chip, together with a G-band LNA, so a 300 gigahertz LNA. And this system has been tested. So it's been implemented and tested at the University of Valencia, and there were 3 test beds. So just to say that the idea was already present at least 7 years ago, so when, let's say, 5G was going to be exploited, at least, but was already there. So, which are the drives, the main drives? The first of all is higher link capacity, and the second one is the lower latency. So we need larger bandwidth, as you know, for sure. And one of the 2 bandwidths that we are focusing is the W band and the D band, first of all. Now, not later on. This is a view of Nokia, it's available, that actually tells us that also to have the peak capacity, we have to go above the W band, the D band, and even above 175 gigahertz, so to be in the so-called sub-terahertz regime. This is one of the drivers. Just to give you an idea that is actually something that we are exploiting already. This is the results of a collaboration that we had with a major telecom company, in which we designed and realized 2 amplifiers, one both covering the full W band for 6G, a power amplifier that you see on the left, and a couple of low noise amplifiers that you see on the right, exactly covering the right bandwidth, so 92 to 115 gigahertz, with quite good performance. And this is with a commercial foundry. This is very important to underline. So we had the access to this technology freely, just paying. That is not trivial. Well, the drives is clearly, for what is regarding you, the 5G advanced, the 6G, and all the services that are forecasted both for the 5G and the 6G. But they are not the only drives for this technology. I would say there are major technology drives, sometimes even bigger than those. And the bigger ones are defense and security for these technologies. Then imaging in general, the industrial sector that is more and more demanding, even from the point of view of normal production. We have been in touch with several companies asking for peculiar performances at 300 gigahertz to verify the properties of materials they produce. So for strictly industrial application, and even for medical. And the biggest investment are driven by the Department of Defense, above all from the US Department of Defense, funded by the DARPA. And this means that we have consequences on the availability and access to the technologies that have been developed and financed by this funding. Well, let's go to the device level, what we are talking about. This is an overview of what can be done, which are the state-of-the-art performances. I would say it is updated to, say, July last year, so there are no major deviation from that. But it's taken from a presentation at the last International Microwave Symposium in Washington. For noise, as you may see, there are the major technologies. We are talking about 5 major technologies. So gallium nitride amps for power, typically, indium phosphide HBTs, silicon CMOS, silicon germanium HBTs, and indium gallium arsenide amps. As you may see, there are several points that underline which are the best performances. For sure, you will see that the best performances are given by indium phosphide related components. So For low noise, indium gallium arsenide HEMS, reaching the terahertz FTF max. And if you look at the power, we are talking about indium phosphide HBTs. These are the two highest performance technologies. While the other one, the most diffused one, the CMOS, let me say, quite remarkable performance up to 150 gigahertz, but much lower than the other ones. Silicon germanium HBTs are slightly better. Technology is not so mature as the previous one, but are indeed worse than the 3.5 technologies. If you go to what has been realized, look at the numbers. We are talking about a realized 1 terahertz amplifier. This is a demonstration that has been done by Northrop Grumman, but we are talking about 2016. Look at the dates. These are quite important. If you look at the indium phosphide HBT, so on the power side, we are talking about an amplifier to close to 700 gigahertz. Again, look at the dates. The latest one is 2017. And this has a meaning, because these technologies have been developed by funding by the Department of Defense. So the usage of this technology is by the Department of Defense, no access at all. Not only amplifiers, but also oscillators, master slave, latch, and other integrated subsystems like receivers and transmitters, reaching, as you see, 600 or 500 gigahertz. So numbers that are quite remarkable. The technology is not exploited anyway, not accessible, and you will not see any product out of those technologies. You may search for products, you will not find them. Well, if you look at lower frequencies, and to say lower is a big word, and look at the Teledyne, that is one of the Department of Defense funded companies, you will notice that you have remarkable performances also at 150 gigahertz. So we are talking about a half a watt amplifier in indium phosphide HBT again. And even if you reach a slightly higher frequency, so 220, you will find something. Always in the same technology, indium phosphide HBT, coplanar waveguide based, and similar design. But the performance is the state of the art that you can get. Even integrated subsystem can be realized. Not commercially available, but they can be realized. And you will see that you have remarkable performances also for, perhaps, remarkable performances also from the point of view of the output power and noise figure. Well, if you look at the window of 140 gigahertz, sorry, but I think it's better to switch it off. Sorry for that. No, it's not me. It's not me.
No, c'è qualche interferenza direttamente nel sistema di amplificazione? Grazie.
Okay. If we focus to the 140 gigahertz window, that is the next, you will see that you have some remarkable performance from silicon germanium realization and HBT realization. But if you look at the performance, you will see those 3.5s that are superior. But if you look at the cost per module, this is not the case. Because if you look at the cost per module, the cost is by far too high if you want to use it in, let's say, commercially viable solutions. So if you look at the number of transistors for the same chip and the eventual cost per module you can get. Well, now let's see how this translates to the technological availability worldwide. First of all, in Europe, if you look at the availability of 3.5 technologies, there are just 2 commercial foundries in Europe. This is UMS and MACOM, now MACOM, formerly OMIC. There are several research labs, but they are not commercial grade, so not usable for commercial exploitation. There are silicon RF and silicon germanium technologies available through the Europractice circuit, but the technologies that are made available are not the top technologies. They are just with limited performance, just to test what is the concept behind. If you look at the USA, you will see that you have the top performance foundries, and all of them have been financed by the Department of Defense. So, with all this means. The big players are not pure foundry, and their technology is not open access. In Far East, Taiwan and Japan, 3.5 up to W-band technologies, no more. So, not usable for D-band and above. In China, no one knows. Several technologies have been exploited. We see some results, but we don't know the details of the technology. And above all, the top performing technologies are ITAR restricted. So even if you have a product, you cannot get freely. You have to be screened for the usage, where it is mounted, and eventually you are authorized to buy it. So it's not a good situation. But the point is that the technology is an issue for intrinsic power and noise, so for key performances. But one needs, at the end, to give a given EIRP and a given receiver sensitivity. So, therefore, the solution may be to use an active phased array for low-performance technology. So, resurrect the usage of low-performance technology, so CMOS, for instance. And once more, if you look at the typical scheme of a phased array, you will notice that you may use several technologies for the same phased array. So, above all, before the first up conversion, you may use the most advanced CMOS, most integrated one. Then you may use the RF CMOS or BiCMOS for all the operations up to before the power amplifier, if we are talking about the transmit side. And you use the top performing technology just for the final stage for the power amplifier. So this depends on the range of frequencies and the applications. But in general, you need several technologies. This is an example what I mean. This is an active phased array system in D-band that has been proposed by ST Microelectronics at the last MTT symposium, IMS symposium, in 55 nanometer silicon germanium BiCMOS by ST Microelectronics. And as you may see, you will see several technologies integrated together for the TX and RX. Phased array, okay, but everything is clear? No. I see many proposals proposing 2Ds or even 3D phased array. But is really 2D necessary? Because 2D means to have several restrictions from the realization point of view. So restrictions that are related to the physical restriction of wavelength and distance between the radiating elements that are alleviated if you use a 1D, one-dimensional phased array. So use one-dimensional wherever possible, because this is the electronic that is behind, that is not viable if you don't. And the beamforming, what is the right beamforming? There is not an answer to that at the moment, because each one, even if you make an RF beamforming, an IF beamforming, LO beamforming, as proposed by some colleagues of the Politecnico of Milano, digital beamforming, so open question. So this is a direction and a trend that is quite well defined. But it's not the only trend. The real big trend in electronics is the heterogeneous integration. These phrases are taken by a speech at the IMS by, let's say, Subsecretary of Defense of the Department of Defense, American Department of Defense. Clearly, the speech has been prepared by someone else. But the main statement is that if it can be done in silicon, it will be. So whatever can be done in silicon will be done in silicon. And this is because the silicon is high yield, manufacturing challenges have been minimized, and you can do homogeneous integration with other silicon-based technologies. But performances are 3.5. 3.5 devices provide superior performance. Then what you have to do is to integrate the two technologies at the chip level, not integrated in a say, module, but at the chip level. this is an example of what has been proposed, integrating a TR module that is on the left in this picture, in a single chip in which you integrate both silicon and gallium nitride. That is a 3.5 technology. This is the MIDAS project is a project financed by DARPA. If I well remember, is a $120 million project in which Raytheon, that is one of the companies, has been financed to realize what you see on the right. So you have a layer that is for the radiating antennas. Then you have a layer for 3.5, so power amplifier, low noise amplifier. Then you have a layer for silicon-based performance on the same wafer, okay? And so the chip comes out of that. But this is just an example, because really DARPA, with this ELGAR program, that is even larger, is promoting the integration of gallium nitride, indium phosphide, both at the HRL laboratories, Teledyne, Raytheon, Northrop Grumman. So we are talking about the big players of the defense industry that are integrating to a different level, different technologies. This is really a game changer, believe me. But not only on the defense side, we are talking about even some big players on the commercial side that is moving. Intel is moving, and Intel is trying to integrate, at the moment, gallium nitride and silicon. And with good results, because you are talking about 300 millimeter E-mode gun technology, so we are talking about wafer scale that are much larger than the actual ones. And these are good news, really. So, some concluding remarks. The first one is that the semiconductor technologies that exhibit peak performance are in line with what the applications, above all in telecommunication, but even in defense, are asking for. But we have a big question mark on the availability and access. This is really an issue. There are two game changers. One is the active antenna array and the MAMO concepts that may allow the use of lower performance technology as the silicon ones, but this is at the expense of overall performance. If you may do the same job with 3.5, you could get much better performance. The heterogeneous integration is a solution, and the right technology is used for the right function, in the same place, in the same chip. One big remark that is important is a call for collaboration, is that we cannot go on with the competencies in a single field. As you may see from the last picture, one of the last pictures that I shown, here we have the radiating level, we have the electronic level, we have the mechanical and thermal dissipation level, so you need competencies for different worlds. The electronic designer is not sufficient to design a chip like that one. So we need competencies and collaborations from different worlds, electronic, electromagnetic, and thermomechanical. We have to integrate competencies, and this is really important even for our courses. Thank you.
Thank you. This situation at global level with a split between Western countries and China, can we then may have a bad surprise of seeing something popping up, and unexpected, and then creating some,
Yes, you know there is a ban.
Yeah, I know.
You know there is a ban, and the ban actually creates some let's say stress on the mechanisms, and the stress creates investments on the other side. Investments that are not clear. Not
Yes.
clear at all. What I know for sure is that the same companies that have been banned are investing very heavily on basic technologies. And they will come up with solutions. And almost sure that in 2-3 years. So close. Yeah, so close.
Other questions? No? Okay. Let's thank Ernesto again.
No, sure.
So the next speaker is Umberto Spagnolini. You will give an...
I'm always impressed of what is doing Ernesto and the direction where we have to go. So, and the last line is really, another another aspect that is missing in our community. So I changed the subject, and you know, in a sense, following the words by Antonio, I go a bit on the imaginary direction. Okay, so after so much real, let me go a bit in the imaginary. So I introduce, you know, in 6G there is this, you know, word that is repeating on sensing, 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 and is one of the main area where, you know, it seems to be a kill application, the sensing part. So let me expand the word on that. So what can I do here? Okay. Okay. So, you know, I discuss about what is the waveform in sensing. I try to put together all the sensing elements in a network. That's because we have a many base station in a system, so we need to put all together. And, you know, and we've been talking about metasurface, so, you know, let's see what we can do with the metasurface for sensing. So let's go one by one. So, you know, I like this picture, you know, because it's giving the, you know, the feeling that there is a connection between communication, which is the first row, and the sensing, which is you know, the lower row. In the middle, there is the way to merge together these two technology. That for sure they have a common background. You know, they're all operating with the waveforms. Huh? So for sensing, we are dealing with the chirp waveform. We are dealing with some accuracy in speed from Doppler. We have accuracy on the range. That depends on the bandwidth. And for communication, we are dealing with the signal-to-noise ratio, with something that depends, the power depends on the distance to the square and so on. So, you know, that's all. So, you know, integrated communication and sensing, or integrated sensing communication, you know, whatever, you know, it has several use cases that are illustrated there, so I don't read. And, you know, inside in our projects, okay, and inside in our group, we have been touching all those that are involved, so many areas. So let me spend a word on the optimization of the waveform. So if we look at you know, what do we have on, you know, on communication? We have the waveform, and the waveform is OFDM, is available, okay? So OFDM, you know, is occupying this panel that is on time and frequency. So, and is transmitting in those areas that are filled in this box. The 8 are representative power. So can we use that? Can we use the OFDM? Well, you know, if you look at that for sensing part, we look at only on the sensing part. If we look at on the sensing part, you know, what we receive and the channel itself is affected by the amplitude, is affected by the variation of the phase, which depends on the Doppler, is affected by some delays that is, you know, contains the information we like, and is related to many targets, capital K. So if we want to estimate now the channel, we want to get from the channel the information that we want to extract. Okay, so the channel is a certain matrix H, and if we want to get back the information rather from the frequency domain into the time domain, and if from the time symbol to the frequency that is related to the Doppler, you know, we need to operate with the Fourier transform. Perfect. You know, if we, I mean, typically the OFDM is not fully filled. So there are many holes. So if we use the OFDM with all the holes that are related to, you know, the user and the resource block that are allocated, we don't get, if we make the inverse Fourier transform, a beautiful sink, but we have something that is more rough, that as you see the dashed line. So, you know, this is a big problem that we have when we want to use the OFDM. So, well, you know, we can write a nice formula, okay? We are very good on that. So we write a nice formula that is, you know, balancing between, you know, the Doppler accuracy and the ranging capability, which is a delay. And then we play with that. We constrain with the you know, the capacity of the system, and we come out with something that is constraining, so assigning the resource of the sensing into this block that you see here. So the yellow represents those areas that are occupied. In the x-axis there is time, and the y there is a spectrum, there is a carriers, okay? So if you look at on the left-hand side, the picture is showing that if you want to make a very nice, Doppler and ranging, in a very good way, balanced, I have to say, then we need to allocate the resources all around, as illustrated there. And if we need to transmit more, then the resources are in the second one. This is indicated B. Do I have the pointer? Or here? Do you see my? Yes. Okay, here. Okay. So on the other hand, if we trade and say, okay, I want to only to estimate the Doppler, I don't care about the ranging, then I need to allocate my resources there on the yellow. Okay. So there is these degrees of freedom. Look, there is an empty space in the middle. So if I don't manage this empty space in the middle, well, I need to find a way to fill that empty space. This is interpolation, you might say. So we can look at this interpolation in a slightly different way. It's a matrix, and we can use, the matrix completion theory on that, and we see what's happened. So all this is another optimization part that we need to do. But, the results are indicated here. So, you can see that if I do the matrix completion, I reach the same performance in terms of, accuracy in time delay that is similar as if the matrix is full. So, good news. Let's go to the network. What does mean network? Network means putting together many, items, many base stations that are cooperating each other. So fine, so we can sense drones, for instance. In Ukraine, perhaps, drones are important, and there are base stations around, and we can use that to spot any drones that are coming in. And we have per people and blah, blah, blah. So, and we can find out how to enhance the performance in this way. So there are some questions that we can ask ourselves. So can we do that, essentially, is this. I understand intuitively that it can be done, but how to do? Well, doing is not easy because I want to have a coherent cooperation. The word coherent, if you remember by the courses that we teach, coherent is everything that is related to the phase, okay? And the phase is by item, by terminals, by base stations that are not synchronized, but usually are synchronized itself locally, but not mutually. So let's live with that. So we have a system where, I have a transmitter on the left and the receiver on the right. The transmitter on the left has some antennas, assume I have N antennas, and the receiver on the right has the M antennas on the other side. So what my problem is now that I want to make a sensing system that is synchronized. So, I'm transmitting a signal on the N antenna and receiving from the others. But, what I receive is affected either by the carrier frequency offset at transmitter, the carrier frequency offset at the receiver, the time offset, and so on. Is affected by many impairments. So, I need to handle with these impairments. So how to do that? So essentially, you might say, when I presented this contribution, and in another country, they said, oh, but it's a synchronization problem. I said, yes, it's a synchronization, but, it has to be shaped, matched with the problem itself. So let's see, what I receive is something like that, which is superposition of many echoes, still at the same one antenna transmitter, one antenna receiver, okay? So what I do is that if I need to let coexist many signals, I can use a very simple way that, I make, each transmitter to use one spectrum, one portion of the spectrum. It's a simplification. I can make it more complex. So, then, I have a scattering, I have the waveform that is received, I have, some time delay, the timer delay that is related to the range, and then I have, the carrier frequency shift, the carrier phase that is affected by some randomness that is used due to the carrier frequency offset at transmitter and receiver. So I try to make the story simple, but you know, what I want to do is that I want to make an image. I want to make an image of where is the target. I don't know where is the target. I make an image in any point of the space, and then I make what is called the focusing. So what is the focusing then? It means that I need to take the received signaling from any antenna and transmitter and any antenna receiver, and then try to focus on every point in the space. Fine. So this one is the formula, the lower one is the formula for imaging. Okay? So, you know, of course, there are some pitfalls I cannot do right away, because I need to have the carrier frequency offset at transmitter, I need to have the correct position at transmitter receiver, and then I need to calculate and compensate for the differential time offset. So you know, I surf over there quite quickly, surf over there quite quickly. You know, if I want to find the complete image, putting together all the transmitting antenna, all the receiving antenna, well, I have a certain phase, alpha, that I need to compensate is there. So this picture is showing you, if I have a single sensor for a single point, this is the kind of image that we see, which is very perturbed by the effect of noise and cluttering. Okay? We use only noise. If we make a monostatic fusion, this is what we see. If you get the multistatic fusion, you know, which is incoherent, this is the kind of image that we get. And if we make a multistatic fusion coherent, we can detect that there were two targets there. So on the upper part are the waveform coverage, but I don't discuss on that. So, you know, and we took several years to reach this result. You might say it was trivial, but, you know, at the end. So there are 3 steps to make this kind of focusing: frequency synchronization, coarse synchronization, and fine synchronization. So let me, you know, is a way to solve an optimization problem, but in a very efficient way. So frequency synchronization is the first step that we have to do. Means that we need to calculate the differential phase, one antenna with respect to the other. This is implying to calculate, you know, a certain problem that we need to solve. It's a system with n square measurement with n unknown. And then we calculate, you know, the absolute phase for every unit up to a constant. Second is to make a coarse synchronization. Coarse synchronization means that if you look at, you know, the image, you need to realign the image one to the other, and there is a roto translation that is the difference between one with respect to the other. So, you know, on the upper part you see before, and the lower part you see after. And then, you know, is the fine synchronization, which is something that, you know, we need to fine-tuning one with respect to the other. We need to spot into the result one permanent scatter, which means one point that is strong enough, and we focus everything with respect to the point, and everything comes focused. So this one is, you know, the visual part. So this one is the experimental result that we made on that. So we have 2 vehicles. Am I late? Okay, I have 2 vehicles, you know, vehicle 1 and vehicle 2. You see the black here, 1 and 2. And, you know, and we are making sensing of, you know, another vehicle with another guy in front. We are using two bands for that. So overall, you know, we have vehicle 1 to vehicle 1 is monostatic, vehicle 1 to vehicle 2 is bistatic, and vehicle 2 to 1 is bistatic, and vehicle 2 to 2 is monostatic. Okay? So this is the ensemble of data that we have. So we applied everything and make the story short. These are, on the left-hand side is, you know, the individual images. The individual image that we get are monostatic, bistatic, and monostatic. If we make a monostatic fusion, this is the result we get, which means, you know, we improve the resolution. But is it really in the right position? Well, if we make the multistatic fusion, you know, it's important that we get this big reflection, that is the corner of the car, because, you know, in sensing, and not everything reflects, only some, you know, bright spot. And here, since the radar was positioned very on the ground, on the bumper of the car, okay, so, you know, we see the leg of the first author of the paper, okay, so which is one of us. So, you know, the leg we are 40 centimeters, we see the leg. So, you know, we are very happy with that. that we covered
the way we use young researchers, right? Like targets in dangerous experiments.
Okay, so, you know, in more details are in the JSAC paper in case, okay? So now I told you that, you know, I go from a little bit real, now I move a little bit in the imaginary part. So our goal was to make okay, there is an error in the font, but anyway. So if I want to make the sensing in a no loss, means that I want to make the sensing behind the corner. So one possible way is that put you know, a plain a metal plate, you know, which is acting as a mirror. Okay, so if is acting as a mirror, I can see behind, right, like in a mirror. But the other way is that I can make you know, a metasurface. The metasurface is acting as an ensemble of mirrors. These ensemble mirrors can be tuned to focus on some points. So, but you know, if I look at these ensemble mirrors, I can only focus on one individual point. Now, what about if I make the mirror, you know, static and I move myself? So if I move myself, then I spot a different area of this anomalous mirror, which is, you know, is a sweeping different area in the blind, in no loss area, so in the blind spot area. So, well, you know, I can generalize this concept, and then I can look at what is the result, the difference. So the first one is when I look at the point behind the mirror. Okay, nice. This is what happens when I put together all this information, but I don't move. So that means I designed this mirror in a proper way to spot the point. If you like, we are in near field, you know, following, you know, the previous presentation. If I make this stroboscopic, what is a stroboscopic? Means that I move, and in the meantime, when I move, I mirror a different point in the space. So I replace the dynamic metasurface with the static one by moving. And the results are in the bottom. So, you know, if I want to put all together, this is the nice result we put together. So, you know, and in the left-hand side is the result by stroboscopic sensing, which is putting together a different image from a different point, and the mirror is on the right-hand side. So the left side is stroboscopic, and the right side is the mirror. So the paper is under writing, you know, it's almost complete, and we think that we can submit very soon, and it will be on archive in case. So, you know, this is closing my presentation. Thank you.
Very interesting. No other question? You know, you said you were going in the imaginary direction. I think it's really interesting for a number of real applications indeed.
It is.
Not really only imaginary. From a point of view of you know, the way, I mean, since basically this is done without much coordination from the transmitter, right?
Which part do you mean?
The first part, right? The part on which you don't use the synchronization and then.
Yes.
Yes. Then you know.
But the only is that when I transmit, the other should receive.
Yes.
So there is a coarse synchronization on transmitter receivers on the duplex side.
So this can enable application also from, you know, from the security point of view can be interesting because of course you have, you know, someone that is able to stay in the environment, start passive listening and looking and then maybe understanding how to make this coarse synchronization and steal information even if you don't want to reveal this information. Somehow this is intrinsic in the technology, right?
Well, I need to agree on what is the waveform.
Okay, maybe you know, because...
well, I can make, you know, following also, I can make, you know, a pattern on the waveform, on the OFDM symbol, or I can design the waveform in a proper way, but, you know, I don't know what is the pattern. So okay, I can randomize the pattern in such a way that, you know, I don't really see what is transmitted. I can infer.
But some known symbols, in some part of the frame are transmitted.
There should be. There should be.
So somehow, you know, okay. But again, also this is an interesting way of looking at this kind of technology. Let's thank Umberto again. The next speaker is Alessandro Fonte, CI Microelectronics. Then for sure we will stay on the real axis, right?
Okay. So following the Ernesto's presentation, I will go back to the hardware, and in particular to the front end for telecommunications. Actually, I will start my talk introducing the Shift project, and we will focus on two demonstrators, one for SATCOM application, the electronically steerable KA antenna, and the second one more related to the telecom market. We are working on this project with several partners, including the Institute of Electronics, the University of Pavia, the University of Roma La Sapienza, the University of Calabria, the Politecnico of Milano, the CLT, the University of Côte d'Azur in France, TESAT in Germany, the University of Roma Tor Vergata, and the University of L'Aquila, MTR, and Planetech. So,
maybe it's good mentioning that CI is entering the Restart program through the cascade calls, and then of course the goal is bringing in Restart the experience gained in other projects. Right?
Yes, exactly. So just a few words regarding the Shift project. The Shift is a sustainable technologies enabling future telecommunication applications, and the main objective is to develop silicon, germanium, and gallium nitride technologies, and also innovative solution for packaging in order to define also demonstrator for telecommunication market, optical speed links, satellite communication, and Earth observation. The project started in December 2022, and the duration is 3 years. It's a quite big project with 43 members from 8 different European countries with a total budget of 67 million euros. So this is the value chain of Shift, so starting from the material for packaging and for the integrated process through the ref design and the package design up to the final demonstrators. So, okay, here there is just the media. And, okay, CIE in this project with the project partners is working on 2 demonstrators. The first is a new solution for advanced millimeter wave components conceived for high-capacity communication, and the second one is the KA transmitting phased array tile for the SATCOM applications. So I can start to talk from the first demonstrator. So the background is the satellite-based Earth observation technologies. So there is a wide range of applications for this kind of system, from monitoring land, maritime, atmospheric conditions, etc. And the request is to increase the demand of data rate from space to ground. So the goal of our demonstrator is to enhance the data transfer from the space to ground, and so meet the demands for high quality Earth observation data. Okay, as I already said, the CI, the project partners are developing KA transmitting phased array tile involving new technologies for the active part, so by using silicon, germanium, and gallium nitride technologies, and also to design a custom package in order to integrate both technologies. Okay, in this slide there is shown the state of the art, the proposed solution, and the innovation. So the state of the art is related to the use of a X-band, a single antenna, a single horn antenna, and a mechanical steering. The technology used is the traveling wave tube. Our proposed solution is more focused on the KA band and a distributed array for the antenna with an electronically beam steering. in this case, the technology is a single package with integrated silicon germanium and gallium nitride. About the innovation is related to the high data rates, the compact size, reconfigurability, and scalability. So in this slide, there is a picture of our idea, and so the proposed architecture is tile-oriented. So we would like to design a single tile that can be multiplied in order to build the phased array antenna. So each tile must integrate all the functionality, so the ref, the bias, the phase shifter, and the amplitude control, and so on. And all these functionality are integrated in a single package that will include the silicon germanium and gallium nitride for the power amplifier. In this slide are also shown our idea of the demonstrator with highlighted the RF section, and also a building block diagram of the package. So the breakthrough is the cost reduction, efficiency, performance, and the integration. Regarding the system architecture, we are working with the first prototype, and the concept is a 64-element TX phased array antenna at K band. In the slide are shown the building block diagram and the first development of the first prototype. Our idea is to have everything ready in order to make measurements before the end of this year. Regarding the active part, the University of Tor Vergata is working on the power amplifier in the Ka band frequency range, and in this slide are reported some specification, and also a picture of the layout and the simulation results that are quite in line with the requirements. The power amplifier has been designed in gallium nitride technology from UMS, and from this design we will expect measurements result in the next month. So this conclude the first demonstrator. The second one is the D-band phased array antenna for 5G backhaul. So this is the scenario. This is our idea. So the demonstrator is dedicated to the development of advanced millimeter wave components conceived for high capacity communications. And our idea is to design the key building blocks. The key building blocks, namely antenna in module at D-band. So why D-band in our case? Since the advent of the 5G and in the future 6G will bring with a huge traffic data, and in order to find more spectrum, we have to move to higher frequency. And considering that today the highest frequency band in commercial use is the E-band from 71 to 86 gigahertz, we have to look beyond the 90 gigahertz, and the D-band, that means 130, 175 gigahertz, is a good option. So we can use the D-band and also the silicon germanium process in order to design all the RFICs for the phased array antenna. Regarding, since we are a company, we have a look also at the market, and in this slide is reported the forecast of the European installed macro cell backhaul links at W and D band. So we can expect that something commercial at D band will start soon. So we are working on it. So why the D-band? Since the high capacity that can be reached, since there are more than 10 gigahertz of spectrum available, the possibility to have a very large channel bandwidth up to 5 gigahertz, And also, since the link will be licensed under a light license process, so that the licenses can be obtained quickly. Okay, this is our idea of the tile, of the basic element of the phased array antenna. This we call it the antenna module, and it is a custom package where on top we would like to integrate the antenna. So we have to develop all the RFICs in silicon germanium process provided by ST Microelectronics. ST have to improve the industrial grade of that technologies. And also we have to think about a new package solution in order to integrate silicon germanium RFICs and the antenna. Regarding the antenna, we are working on the first prototype of the antenna, and in this slide I reported some information regarding the antenna, the 4-in-line antennas, and the first simulation results. Also in this case, we plan to have the first measurements before the end of this year. Regarding the RFICs, we have a lot of developments, mainly related to the RFICs designed in silicon germanium by Siemens 55 nanometer, and we are talking about transmitter, receiver, phase shifter, feedback path, and also synthesizer. In the first part of the project, the University of Roma La Sapienza are working on the down converter. So in the first test chip, I've designed the down converter from the D band to baseband. And in this slide, I reported the first test chip and that table with the post-simulation results. And for this design and the follow, we will expect measurements results in a few months. Regarding the up converter chain, the University of Pavia designed the mixer and the power amplifier at the band, and in this slide I reported some simulation results compared to some measurements result of mixer and power amplifier already designed in a previous run, in a previous version of the technology. Finally, the Polytechnic of Milan is working on the local oscillator and the sextupler, and in this slide I reported some information regarding the two components. So we are still working on the building blocks on the antenna and on all the building blocks are okay at the moment. We are waiting for the measurements, for the first measurements, but the project is in line. And if I have one minute, just to say that, okay, we are working at the band, we have a lot of ideas, but this demonstrator followed another project in which we have been involved, named Taranto. So, and in particular, this demonstrator that is an advanced multi-gigabit band transceiver front-end 4mm wire backhauling, and also in this case the goal is the point-to-point link, and the partner almost the same, ST, Politecnico di Milan, the University of Rome, and the University of Calabria. The focus has been the E-band, but at the end of the project we designed the RFICs, we designed the test board, and we had integrated everything in our radio in order to make some characterization of this, in this case the receiver. And at the end of the project we made also some measurements. Here there are two different tests. The first one with several different modulation scheme, and the test U is more focused on the check of the VGA control that has been included in the receiver. So,
thank you, Alessandro.
thank you.